How's it going, ladies and gentlemen? It is Mr. Donahue here again, taking a look at 25.7 chirality. So our objectives will be to identify the location of chiral centers in organic molecules as well as explain their significance. All right, well, what is chirality? Basically, chirality is when a molecule has a non-superimposable mirror image. So it's kind of like a left hand and a right hand, right? They're mirror images of each other, but you can't superimpose them. You can't lay them on top of each other and make the same thing. That's why left-handed gloves are different than right-handed gloves. They're not the same. They're different. So chiral molecules have that same kind of thing going on. So if we take a look at this here, I have a carbon center, and then I have four different things on it. And next to it, I have the mirror image. Now, this mirror image, there's no way that you can superimpose them, lay them on top of each other and get the same thing. Because even though they have the same parts, they're connected and arranged in 3 dimensions differently. And that's what chirality is. So it's like a left and right-handed glove. Cool. So watch me try and superimpose these things and the frustration that ensues, okay? Just watch. Play. Ready? Oh, first find how they're mirror images. Okay. All right, well, nope, can't lay them on top of each other. What if I turn it and try it this way? No, then that doesn't match up. And I'm going to, nope, it doesn't work. Despite all my efforts, I can't do it. All right. So chiral centers. So the location where chirality exists is called a chiral center. So, taking a look at this one, this carbon right here is a chiral center. I'm going to put an asterisk next to it because it has 4 different substituents. And if I switch like the hydrogen and the bromine from going away versus coming towards, then I end up with a different molecule, or a molecule with them arranged differently in 3-dimensional space. So when do you know it's chiral? Basically, when you have a non-superimposable mirror image. So you can look at it and go, hey, here's a mirror image of these 2 molecules. Can I superimpose them? No, then you got a chiral molecule. And that typically happens when there's a carbon with 4 different substituents on it. So if I take a look at this carbon, I got 1, 2, 3, 4 different things on it. So that's going to be a chiral center for carbon. All right. So find the chiral center in this molecule. So you should be looking at this molecule and you go, all right, well, this carbon only has 2 different things. I got hydrogen, which is one kind of thing, and a carbon chain, which is a second kind of thing. So that only has 2. So it's not going to be that carbon. Middle carbon. Well, there's a carbon. That's one kind of thing. There's a hydrogen. That's a second kind of thing. There's another carbon. And there is an OH, which is only a third kind of thing. Interesting. So this molecule, not really chiral because it has 2 identical things. Right here, this CH3 is identical to this CH3. So this carbon cannot be chiral. This molecule has no chirality. Let's take a look at some more examples. Is it chiral? So here I got a carbon with 4 hydrogens on it, but that's only one kind of thing, so no, that's not chiral. Here I got a carbon with 1, 2, 3, 4 different kinds of things, so that will be a yes, that's chiral. All right, here I got 2 different carbons I got to look at. I got one, the first carbon has only 2 kinds of things. It's got hydrogen and then a carbon thing on it, so there's only 2 kinds of things. That one's definitely not chiral. So let's take a look at this carbon. This carbon, I got a hydrogen and a hydrogen, so that's only one kind of thing, and then an OH group, that's a second kind of thing, and then a carbon group, which is a third kind of thing. So this one is not chiral either. All right, what about this carbon? All right, well, I got a chlorine, which is one kind of thing, carbon chain, which is a second kind of thing, and a fluorine, which is a third kind of thing, and another fluorine. So there's only 3 kinds of things, so these ones are not chiral. All right, well, let's take a look at this stick model. So I know that there's a carbon right here, and on that carbon there is fluorines. Oh, hey, there's more than one fluorine. They're the same kind of thing. So I know that one is not going to be chiral. Well, what about this carbon? Well, there's a chlorine, there's a bromine, there's a carbon chain, and then there's, not drawn in there, is a hydrogen. So this one is definitely chiral. Yes. All right, so properties of chirality. Rotating the plane of polarized light. So if I had polarized light, and let's say I'm going to pick an arbitrary direction, it was polarized in this direction. So if I got polarized light, it's, wave is going in this direction. If we had that polarized light go through chiral material, it's going to rotate that degree of polarization. So right now it's polarized in this diagonal direction. If it goes through a just a chiral stuff, it's going to rotate that so it'll be maybe rotated in this direction. So it rotates polarized light. All right, so here's a big chart that's probably going to overwhelm you. I'm going to walk you through it. So this is all about isomers and stuff. Are they isomers? What kind of isomers are they? So it has to do with different arrangement of atoms. So first things first is what we call conformers. Basically, it's a different arrangement from single bond rotation. So it's saying, hey, if I got butane and it looks like this, or does it look like this? This is not an isomer. Conformers are not isomers. They're just rotated to give you a different shape. It's an arrangement around a single bond just from it twisting. All right. So now let's talk about isomers, where we have it. Actually, we have different bonding. So there can be different kinds of isomers. One is the structural or constitutional isomer, where you have different connectivity. So that's like if I had butane and then I went, hey, now instead of that I got methyl propane. This would be an example of a structural isomer. We actually change the bonding, right? Then we have stereoisomers, where it has the same connectivity but different spatial arrangements, and I'll show you what I mean by that. So we have enantiomers, which is pretty much just what we were talking about. We have a chiral center. We have 4 different things off a carbon, and this one is a wedge coming out towards you, and this one's going away, and then we have the mirror image of that, which is going to be different. All right, you get it. We just talked about that whole bunch. So enantiomers is when you're talking about different forms of a chiral molecule. Then we got diastereomers, which they're not mirror images. So they have different spatial arrangements, the same connectivity, but they're not mirror images. So things like geometric isomers, where you have cis and trans. So I can have something like, trans difluoro 1,2-ethane, or I can have it be the cis version of it. So those would be examples of geometric isomers. And then we have another group where it's just there are 2 or more chiral centers that are not mirror images, and we're not going to really talk about those right now. Cool. So chiral isomers, they have identical physical properties because they have the same connectivity. They're just arranged differently in 3-dimensional space. So they have the same melting and boiling points. They also have identical chemical properties when they react with non-chiral reagents. Only then do they have identical chemical properties. And the reason for that is sometimes the chemistry, when you have chiral reagents, the form does matter. It's like, all right, I have this left-handed glove versus a universal glove, the little silicone that you can just slip over either hand. It matters when you have chiral reagents. All right, racemic mixtures. New vocab, not really incredibly confusing, though. It's basically you have chiral molecules, so you know that they rotate the plane of polarized light. Well, if you have a mixture of both chiral isomers, then overall there is no rotation of light. So if I had, the left-handed version and the right-handed version, well, the left-handed version may rotate it counterclockwise and the right-handed may rotate it clockwise, but when you mix them together and you get the left and right, there is no rotation. And that is a racemic mixture. So they cancel each other out. An equal mixture of optical isomers is called racemic. And does it matter? Why? Who cares? It's chiral. Neat. So what? Well, different forms equal different action in biological systems, especially. Commonly, only one form is found in nature, and synthetic compounds may be a mixture of both chiral isomers. So it affects the activity of things like drugs and medicine. If you're, trying to synthesize a drug and you make it synthetically, it may, only be active half of the time. Like only the left-handed version would be, effective in a biological system, and you got to figure out a way to optimize your production. Or supplements. If you ever taken like amino acids or looked at a label on an amino acid, you'll see it says like L whatever it is. All right, so the L is telling you which chiral form of it you have, and the L is the only kind that's active in biological systems. So if you made that amino acid synthetically, you get a mixture of both. Only half of it's going to be effective. So what can you say? Summarize. What can you say about chirality and properties of chiral molecules? How to tell if it's a molecule is chiral? How can you tell if a molecule is chiral? Okay. and why does chirality matter. All right, so I hope you found this video helpful. I'll see you in class. We'll play around with models and stuff so you can see chirality for yourself. All right, okay, bye.